Third Law of Thermodynamics. How much information do we need to fix the state of a system? In discussing this, we are going to state two new postulates. The first is known as the Third Law of Thermodynamics. The other is known as the state postulate. If we have a pure substance and we cool it down to absolute zero, all its molecules occupy their lowest energy state. Once this happens, we have only one microstate possible. So at t is equal to 0 K, omega is equal to 1. In this case, the entropy, which is K ln of omega, would be 0. The entropy of a pure substance in thermodynamic equilibrium is therefore 0 at a temperature of absolute 0. Now, in classical thermodynamics, where we do not talk about what is happening at the molecular level, we cannot prove this. We have to accept this as a postulate. And this is what we will call the third law of thermodynamics. If we want to calculate the entropy of a system, what is the minimum amount of information that we need? For a monoatomic gas, we had already shown that S is a function of U, the internal energy, V, the volume, and N, the number of molecules. Now, N is proportional to the mass M of a gas. So we can write that S is a function of U, V, and M. The fact that the entropy is a function of U, V, and M for a monoatomic ideal gas is something that we obtained using kinetic theory and quantum mechanics. How do we do this if we are dealing with classical thermodynamics, where we do not talk about what is happening at the molecular level? Now we must know the mass, M, and the energy of a system to fix its state. The energy can be changed by either work or heat. And we therefore need one variable for each way the energy can be changed to fix the state. Now, internal energy is one such variable. If it's a simple compressible system in which the volume can change, then we must know the volume to give the amount of boundary work that has been done. If there are other work modes which are possible, for example, shaft or spring work, then we need one variable, which we're going to be denoting by X, for each one of these work modes. So in general, the entropy S would be a function of M, U, V, and for one variable, X, for each different work mode besides boundary work. Now, if we confine ourselves to just a simple compressible system, then the only work mode is expansion or compression. The amount of work done is determined by its volume V. So let us give what is known as the state postulate. And this states that the equilibrium state of a pure simple compressible substance is completely described by its mass M, the volume V, and internal energy U. So we can write that as the equation that S is a function of U, V, and M. Now again, in classical thermodynamics, this has to be accepted as a postulate. It cannot be proven. So this equation, S is a function of U, V, and M, is known as the fundamental equation. And in principle, this contains all the information necessary to calculate the properties of a system. Now we have seen this written down for an ideal monoatomic gas. But for more complicated systems, we usually don't have enough information to write this fundamental equation. So what we are going to have to do is relate the entropy to properties such as the temperature, pressure, and volume. And by measuring these intensive properties, we'll have to calculate the entropy. Now we can also define an intensive property, which is the specific entropy. S, which is the entropy divided by the mass of the system. The fundamental equation, if we write it in terms of intensive properties, is then S is a function of U and V. By rearranging this, we could also in principle write U as a function of S and V, or V as a function of U and S. And in general, the state of a simple compressible system is fixed if we know any two independent intensive properties. To summarize, the third law states that the entropy of a pure substance in thermodynamic equilibrium is zero at a temperature of absolute zero. The state postulate states that the equilibrium state of a pure simple compressible substance is completely described by its mass, volume, and internal energy. The fundamental equation for any system is S is a function of U, V, and M.